Hello, everyone, and welcome to this exam revision webinar for MT1186 mathematical methods. So what we're going to do today is focus on solving exam style questions. So if you want to grab pen and paper or a tablet so that you can jot down some calculations as we go along, then please feel free to do so now. And we're going to start with a question on the method of Lagrange multipliers. Question reads, consider the function f of x and y equals 1 over 81 x squared y cubed, and the region R defined by the inequalities that x and y are greater than 0 and x plus 2y is less than or equal to 15. And the first task is to sketch the region R and some contours f of x and y equals c on the same axis. Now here I want to start with a preliminary working here. So let's say that I don't know what these contours f of x and y, that is 1 over 81 x squared y cubed equals c, are going to look like. So let me investigate the curves. Let me call this just a prelim here. So as it says in the question, we know that contours have equation f of x and y equals c. And x is greater than 0 and y is greater than 0 as given in the question here. So c is greater than 0. And now I can solve for y here. To see what we get. Okay, 81 over x squared, all raised to the power of a third. And let's just simplify this here, where we call this a times x to the minus 2/3, where a equals 81 to the c to the 1/3. Or have I lost the c there? I see that that was not. So here there should be a c. Let's see. A is 81c to the power of 1/3, and that's greater than 0, just to simplify the expression a little bit. And now let me look at the first derivative here in order to determine whether y is increasing or decreasing. So differentiating y equals ax to the minus 2/3, where a is some positive number, as we said. Well, we have the power comes down. The power is reduced by 1. And we see that, well, for all x, and in particular all x greater than 0, which the ones we are interested here, well, this is negative. Since a is positive, this is always positive here, x to the minus 5/3, but then it's multiplied by the negative number, minus 2 over 3. So this y prime is negative for all x greater than 0, which means that y is decreasing. And now let's look at the second derivative to see whether these curves are convex or concave. So the power comes down, and now the two minuses here multiplied give us a plus. Power is reduced by 1. And now we see that this expression here is greater than 0 for all x greater than 0, and so y is convex. Finally, let's look at limiting behavior. And if you just joined, for those of you who joined a little bit late, like I said earlier, I'm just doing a preliminary in this question. Let's say that I don't know how to sketch these contours f of x and y equals c, and I need to do some calculations so that I can sketch the contours and then the region R, right? So that's what we are doing here. And so as x goes to 0 from the right, what happens to y? Let's remind ourselves of what y is. Perhaps now it's useful to write it in this form here. And so the denominator there gets closer and closer to 0, and y goes to plus infinity. And what happens as x gets larger and larger? Well, then we can see that y here goes to 0 from above. And now we are ready to sketch. So that will be the answer to part A. Now, in order to save some time here, I have done some preliminary work, and I'm just going to import the sketch here to save us time. So let's just go through this here. First of all, I've sketched the region R, and let's write down the working for that. So this is the line x plus 2y equals 15. I just need 2 points on the line to sketch it. So a convenient value to choose of x then is just x equals 0, which gives us that 2y is 15 and therefore y is 7.5. And when y equals 0, then x equals 15. So that's that here. And you see that I've dotted the line here. The lines y equals 0 and x equals 0 are not part of the region R. So the axes there are not part of the region R, but everything in it, and then including the boundary, which is the line with equation x plus 2y equals 15. Well, those are in the so-called feasible region. And then I've sketched the contours here. And very important, as you can see here, the direction of increasing C values. And so this contour, if I call the bottom one here C1, well, C2 has a greater C value than C1. C3 has a greater C value than C2, and so on. So remember that contours here, they indicate the output of the function here. And so you can see here that this product here, 1/81 x squared y cubed, well, it's increases here in this direction. And I would like to point out, of course, that contours, if I hadn't written my preliminaries, I would now add that contours have equation f of x and y equals c. Now, of course, this question has another two parts, as you can expect. And so let's get ahead of ourselves now a little bit by seeing here this point here of intersection between a contour of the function f and the feasible region R. And that is right here. And what is this point here? Well, of course, it is the maximum. It's the point where the maximum occurs when we want to maximize f of x and y here, that expression subject to the constraint that the point xy should be in the region R. And that will be the next question. By referring to your sketch in A, explained by why the method of Lagrange multipliers can be used to find the maximum value of f of x and y subject to the constraint that the point xy should satisfy the inequalities, as we've seen here, that define the region R. And so here we just do a little bit of writing, and then of course part C will be to find this maximum, both the point where the maximum occurs and the maximum value of f subject to this constraint that the maximum point here should lie in the region R. So what we've learned in the course, that the method of Lagrange multipliers can be used as there is a value of C. In my sketch, that's C2, where a contour of F is tangential to a boundary of R. And which boundary is that? The line with equation x plus 2y equals 15. And just going back to the sketch, as we can see here. And the Lagrange multiplier method can only be used for an equality constraint. So now we have this inequality here, constraints that we have reduced to an equality constraint, because we know that the maximum occurs here on the line x plus 2y equals 15. And so now then moving on to part C, hence use the method of Lagrange multipliers to find the maximum value of f of x and y on R. So I'll give you a head start there to write down the Lagrangian, just so that you can see where you stand at this point in your revision. Just take a head start. Remember that f of x and y equals 1 over 81 x squared y cubed, and the constraint is x plus 2y equals 15. Okay, I think that's probably enough of a head start to write down the Lagrangian. And if you didn't remember how to set it up, well, then we're going to clarify that now. So the Lagrangian is a function of x, y, and lambda. We start here by writing down the function we are optimizing. Doesn't matter if we are maximizing or minimizing. In this instance, we are looking for the maximum here, but we write down the expression for the function f first. And then we write minus lambda. We arrange the constraint x plus 2y equals 15 in the form x plus 2y minus 15 equals 0. And we write x plus 2y minus 15 here. And then let's also set up in general terms, what's the system of equations that we need to solve now? And as you know, we find all the first order partial derivatives of the Lagrangian and then set those equal to 0. In general, these partial derivatives are functions of x, y, and lambda. So in other words, what are we doing? We're finding stationary points of the Lagrangian. That's what we are doing here. So now the setup is very clear. The examiner can see that we have a clear aim, and we have also told ourselves what we need to do. So the rest now is in partial differentiation and then solving this system of simultaneous equations here. So starting by finding then the partial derivative of L with respect to x, we treat y and lambda as constants. So the power of x here comes down, the power is reduced by 1. Y cubed, remember, y is treated as a constant, so that stays there. And what do we have left here involving x? Well, we only have minus lambda times x. And so differentiated with respect to lambda. That's minus lambda. And that's the first equation in our system. Now take a little head start to find the partial derivative of L with respect to y. We now treat x and lambda as constants. Okay. Now, the power then of y will come down. The power is reduced by 1. X squared stays the same. It's treated as a constant. Okay, that's that term dealt with. What do we have left involving y? It's minus 2 lambda y, and so differentiated with respect to y, get minus 2 lambda, and then we set that equal to 0. Now, the final partial derivative then that we need to find is L with respect to lambda, and of course now x and y are treated as constants, so this first term differentiated with respect to lambda, that will give us 0, and all we have left here is minus times this whole bracket here, set that equal to 0. And of course, this is nothing but the constraint here. Just rearranged, multiply both sides by -1 to get rid of the minus sign, put the minus 15 there, add that 15 to both sides, and we come back here with the constraint. So we might as well write it in this form if you like. And what do we want to do now? Well, now we want to eliminate lambda from equations 1 and 2 so that we get a relationship between x and y that we can substitute into equation 3. Then equation 3 will become an equation in only one variable so that we get a solution for either x or y depending on how we do it. And then we go back to the relationship we found between x and y to find the remaining variable. And it can be useful, at least while you're doing revision, until you are completely solid on the method. Why not write down what we are doing here? At least I find it useful. So eliminating lambda from equations 1 and 2. Well, first of all, I'm not going to write it here just to save some space for this presentation, but lambda equals 2 over 81 xy cubed, and then we have 2 lambda equals 3 over 81 x squared y squared. And so we need, in order to make lambda the subject, we then need to divide here by 2, so lambda equals 3 over 2 times 81 x squared y squared, and then we can equate these two expressions for lambda. I'm just gonna write it like this, 2 times 81. You can see here these 2's are going to cancel anyway. So let's see, let me give you a head start to just progress a little bit with that. Just multiplying out here. I said the 2's were going to cancel. That's not what I meant, obviously. Sometimes I talk and I write and it it doesn't come out right. So we get, if we do it here on the left-hand side, we get 4xy cubed, depending on how you do this. And then you're left with 3x squared y squared on the right. And now we know that x and y are both strictly greater than 0. And so we can divide by x and y as we please in order to simplify this. So I'm just writing a note here. Let's see what I want to do. Depending on where I want to keep the fraction here, I can multiply by 1/3 and then x to the -1, which is the same as dividing by x. And then y to the power of -2, same as dividing by y squared. So let's see what that gives us. I'm then left with 4 over 3y on the left-hand side and just x here on the right-hand side. Of course, it doesn't matter here how we express this, but this is a relationship here between x and y that I was talking about that we now can substitute into equation 3, so that equation 3 becomes an equation in one variable only. And since I expressed it here with x here, and we have x here in the third equation, well, it's convenient then to make equation 3 an equation in y only, the way that I did it here. But of course, you are free to do it differently. It doesn't matter. I'm just going to put sub into equation 3. And now it's just a matter of pulling all of this together. And we should get here 10y over 3 is 15. And so y star is 45 over 10, or 9 over 2. Okay, I see I had a message in the chat, something's internet cut out for a bit. If I can repeat the last part, assuming that was from here onwards somewhere, where all I get, yeah, the last result here is just by simplifying, we have equated the two expressions for lambda. That led us here. Now we want to simplify this as much as possible. And so I said, since x and y are both positive, we can certainly divide by x and y as much as we want. And I did just that. I divided by x and y squared, and then I also multiplied both sides here by a third, just to get rid of here this 3 and make x the subject. But this, how you do that, is up to you. The point is that we get a relationship between x and y now that we can substitute into equation 3. So basically, in other words, it tells us 4y is 3x, right? So if we had 3x appearing here, well, then we would say, well, 4y plus 2y is 15, right? So you don't need to make x or y the subject per se. You just get a relationship between x and y that you then can sub in here. Okay, you're welcome. All right, so now we have the value of y that maximizes the expression for f of x and y subject to the constraint that x plus 2y must be 15. Now we go back to this here. How should I write it? Let's see. Back here to find x star, which is 4/3 of y star. And so that's 4/3 times 9 over 2. And so we see that x star is 6. Okay, so that is the point xy where the maximum occurs, right? But we haven't found the value of f there yet. Now we need to evaluate f at x star, y star. Before I do that, let me point out here. So remember we talked about here we're finding critical points, or stationary points as we call them, of the Lagrangian. It is of course possible for a Lagrangian to have more than one stationary point, right? So if you get that in the exam, and that's why we sketch here, right? And the examiner is going to ask you for the maximum or the minimum. So it's the sketch that helps us do that. It both helps us to see that the Lagrangian, to justify that the Lagrangian method can be applied as we answered in point B, but also by seeing here, we've put the direction of increasing C values here, right? And we see that these values increase as we go in this direction. So all of these, so on this contour, the outputs of F are all C2, whatever the value of C2 is, which we're going to find in a moment. But it's only this point of tangency here with the region R that where the constraint is satisfied, right? The other points here on C2 aren't in there. So just keep that in mind, that then that can help us see already, you know, if we had several points of tangency or something like that, which one is the maximum and which one is the minimum. So keep that in mind without actually working out the values. Of course, working out the values will also tell you whether something is a maximum or minimum. So now then, in order to answer the question, the maximum value of F on the region R is given simply by evaluating F at the stationary point, which we already know is a maximum. Plug in the values of X star and Y star. And what's the expression of F is 1 over 81 X squared Y cubed. And then just going to work that out. I'm doing it here without the calculator, so let's see. Just going to do it like this. Sort of old school style, if you like. Let's see what we get. Okay, so first of all, this 9 squared is going to make this power of 9. 1 here, this 2 squared is going to make this power here of 2 into 1. And so we have 3 squared times 9. In other words, 81 over 2. Or if you like, 40.5. So that's the value of C2 there. Okay, somebody had asked, where can you find the recording later? So the LSC team is going to upload it to your VLE. Yeah, that is the answer to that. Also, there's a YouTube channel where it's visible later called UOLIP LSC, I believe, but you should find it directly on your VLE under the course. Okay, somebody, your internet cut off in the sub question B. Can you go back so you can look at it? Sure. This was just justifying why the method of the Lagrange multipliers can be used to find the maximum value of F and X and Y subject to the constraint that the point XY should satisfy the inequalities that define the region R. You're very welcome. Okay. Now, on to something else. Question 2 here reads, use row operations to determine the values of the constants lambda and mu, getting fancy with Greek letters here, if any, for which the system of equations that we see here, x plus 2y equals 2, 5x plus y plus lambda z equals 7, and x minus y plus z equals lambda, has no solution, exactly one solution, infinitely many solutions. And question asks us here, for the values of lambda and mu you found in part 3, express the solution to the system of equations in vector form. Okay, so we know that definitely there are values of lambda and mu that for which this system has infinitely many solutions. But now we need to do row operations then, and so we want to create the augmented matrix. Now, of course, in the exam, to save time, go straight ahead and write down the augmented matrix. You can do that while I write down the system in matrix form, because that is, of course, where the augmented matrix comes from. Since we're doing revision, let's just make sure that everybody is sure about how to write this system. in matrix form. Okay, so we're going to have a coefficient matrix, 3 by 3 matrix here, since we have 3 equations and 3 unknowns. Can call it A if we want to give it a name. And then we have the vector of unknowns underlined here to show that it's a vector. So that's x, y, and z here, and then right-hand side B. And so it's called coefficient matrix for a reason, because what goes in row 1 here? Well, just the coefficients of x, y, and z in the first equation. And then we write down the right-hand side. And similarly for the remaining rows here. Okay, so that's the system in matrix form. And now we, of course, like I said, we would start here the question just by writing down the augmented matrix directly, and then start doing row operations. We can separate out the right-hand side B here with a line. Okay, so I have a so-called leading 1 here. In the first row, I want to make zeros below that leading 1. So my aim here is going to be, at least when it comes to evaluating the solution set, it's going to bring this coefficient matrix up into so-called upper triangular form, where we have all zeros below the main diagonal. But furthermore, I actually, for when we want to write out the infinitely many solutions later, of course, I also want to have leading ones wherever I can, and eventually have that matrix in so-called reduced row echelon form. But we'll see that later. For now, just going to start doing row operations. It is useful, I think, to write them down so you can see what you're doing. If you have to go back and correct the calculation, then you immediately see what you've done. Okay, so row 1 I'm keeping fixed. And I can now add or subtract as suitable multiples of row 1 from rows 2 and row 3 respectively, so that create those zeros that I want below. And you can see here that row 2 going to row 2 minus 5, row 1, well, that will make this 5 a 0, and that's what we care about. The rest of the row then will become whatever it becomes when we do that row operation. And row 3 minus row 1, that will give us a 0 there. Okay, so we can just write down row 1. We're not doing anything to row 1. And now just do row 2 minus 5 times row 1. And row 3 minus row 1. And now I would like to create a leading 1 out of this minus 9 here. And so row 2, it's going to go to row 2 multiplied by 1 over 9. The rest of the rows don't change. Okay, so far so good. And now I would like to, like I said, for the analysis part, it's enough to have zeros below the main diagonal. So for now, I mean, nothing wrong with making also this 2 into a 0. I won't do it now, so I'm just going to deal with this -3 here. So row 3 will go to row 3 plus 3 times row 2. See what that gives. Let's just write down the other 2 rows. Okay, then we have 1 minus 3 lambda over 9. One way to write the result is just 3 minus lambda over 3, like this here. And then mu minus 2 plus 1, that's mu minus 1, like this here. And now for the purposes of analyzing, we are going to stop here. So for now, we know for certain that we have created 2 leading ones. But of course now, this entry here in the third row will depend on the value of lambda, whether we have a 0 or a non-zero entry there. So for now to analyze, we're going to stop there. So have a think about now, are there values of lambda and mu for which the system has no solution? So you need to look at this here, and in particular, of course, here we need to focus on the third row. Have a think about that. And what would that look like? Well, if this row here, if lambda is such that this entry here is 0, and mu is such that this entry on the right-hand side is not 0, well, that would correspond to an equation of the form 0x plus 0y plus 0z equals something non-zero. And there aren't any values of x, y, and z that can satisfy that. And when does that happen? Well, if we could write down this in equation form here, like this. So if 3 minus lambda over 3 equals 0 and mu minus 1 is not equal to 0, which is the same as saying that if lambda equals 3 and mu isn't equal to 1, then the system has no solution. So there's no common point or line or plane of intersection is what that means. In R2, think of 2 parallel lines here that aren't the same line. Well, they don't have any point in common, right? So that would be in R2 an equivalent system where the system of equations doesn't have a solution. There aren't anything, there's nothing wrong with the lines, maybe beautiful lines, but they don't intersect, right? So here we're in R3, we don't interpret that geometrically in the course, but that's what it means, that these planes here in R3 each of the equations represent a plane in R3, and they just never intersect when lambda equals 3 and mu equals 1. Now, how about a unique solution then? Is it possible here that this system has a unique solution? Have a think about it. And again, of course, it's the third row that we have to look at here. Just a head start to think about it. Like I said, just so that you get warm, see where you stand at this point in your revision. It's great if you immediately can think of what that would look like. But if you don't, well, then by thinking about it now and then hearing the answer later, right, then you'll start processing that. And then, so hopefully you walk out of the revision webinar having learned something and being a little bit further ahead in your revision, right? So that's my goal for the session. So that's why it's good to think about it. Nothing wrong with being stuck, and then hopefully we'll get unstuck. Okay, just a little bit more time to think about it. Okay, so for a unique solution, well, then we know that we would have to have a third leading 1 here, right? Because then our coefficient matrix A would be invertible. And so 3 minus lambda over 3, well, as long as it's not 0, then we can divide by that entry, whatever that non-zero number is, we'll divide by it in the next step to create a leading 1. So the most general answer is that this entry cannot be 0. And is there any condition on mu then? No, of course there isn't, because then the right-hand side here can be anything. Once you've created a leading 1, whatever the right-hand side is, well, that's the value of Z that solves the system. So 0, non-zero, it doesn't matter. And so one way to say that, we just want to highlight that I know that there isn't any condition on mu, well, is that mu is just any real number. And now we can say, of course, this more specifically. So if lambda isn't equal to 3 and mu is any real number, then we have a unique solution here. Okay, question in the chat for the notation of Ax equals b. Do we have to put the line under x and b suggesting is a vector? Well, I would highly suggest that you do so, right? Because that is what, if you use that notation, I mean, you don't need to, call this anything, right? But if you have any question where you're writing that notation, so what's the problem, for instance, of writing b and not b underlined? Well, b looks like a scalar then, right? It just looks like a number. So that's why we underline it. So that's when you see it typed, you see the vectors in bold, right? So it's to help us distinguish the scalar x that I put in here, for instance, are these just take real values versus that this vector x is the vector xyz action. So that's why we do it. It's for clarity. So now we know that there's a positive answer to question number 3 here, because we are going to write out the solution in vector form for these values of lambda and mu. But then just take a head start on writing down what's the value of lambda and mu for which this system has infinitely many solutions. And then we've basically covered everything else here. So what's left? What could this third row look like now if there are infinitely many solutions? Well, clearly this isn't the leading one here, because then we were in the unique solution scenario, exactly one solution. So this has to be 0. And as we know then, for consistency, we can't have something non-zero on the right, as we talked about in case 1. So the entire third row there in the reduced augmented matrix has to be 0. And so that happens if 3 minus lambda equals 0 and mu minus 1 equals 0, i.e. if lambda equals 3 and mu equals 1. So then we have a row of zeros. What does that mean? I mean, you may wonder, what does it mean? Well, it means that one of these equations, in particular, the third equation in this system, was redundant. It doesn't tell us anything more than the first two equations. So when we do row reductions, so the Gauss-Jordan method of elimination, the Gauss-Jordan method tells us which equations are redundant. It's like if you write down the equation for a line in R2 and you multiply that equation by a non-zero scalar, you just multiply it up and you write down 100 such different equations, right? And if you put those into a matrix, well, you get all rows of zeros below if they were all multiples of the first equations, because they would be redundant, they would describe the same line. And so the system here, the method tells us that this is redundant. Okay, so let's now write out the solution in vector form. Take a head start on that. Well, the first thing we can do is to just write down what the system looks like then. Just take a moment. Okay, so the system would then look like this here. Of course, this row of zeros is really not giving us any information. Now we see here that the variable z can be treated as a so-called free parameter. It can take any real value here. So we can write z equals t, where t is some real number. And so what do we have here? We have that y, second row here tells us that y is a third. If you arrange this for y, well, it's really y minus a third z, but z is t, y minus a third, t is a third. And so y is a third plus a third t. Looking at the first equation, well, the first equation tells us that x plus 2y equals 2. So 2 minus x equals 2 minus 2t, but we then express y in that form. A third plus a third t. And pulling that together, we get 4 over 3 minus 2 over 3 t. And now we can write it in vector form then for x, y, and z. Can write it as a single vector first here. And z is just t. And now we can separate out here. This part here. And t is some real number. So what this actually is here, so this is a line in R3 here where the line doesn't go through the origin, and this point here is where you go from the origin to the line, and with multiples here of this so-called direction vector, you move along the line. Now, somebody asks, is it always the same format for infinitely many solutions? Yes, as a main form it is. However, here there could be another, not in this case, there couldn't be any other scenario for infinitely many solutions, but it would be possible. Now, forgive me if I don't remember if we cover that in this course, but if this wasn't a leading one either, and our second row was also a row of zeros, well, then there would be two free parameters. So y and z would both be free parameters. And then there will be a plane of solutions. So then this vector here, if you split it out like this, would be, if it doesn't go through the origin, then you would have some point here on that plane now in R2, and then you would have plus, say, s times some direction vector plus t times some other direction vector where y equals s and z equals t. But from what I remember, I don't think we covered it in the course, but that for a 3x3 system could have been another possibility. So, you know, as long as there's a free parameter, then there are infinitely many solutions. Doesn't have to be only one free parameter. It could have been two. In this case, impossible here since we have two leading ones and only one free parameter. Okay, now somebody asks again, where can you find a recording of this webinar? Well, it will be posted on your VLE by the LSC team after the session once I send through the recording link. And also there's a ULIP LSC YouTube channel, but you can just go to your LSC to see it. Your LSC, sorry, your VLE. Now, need to do some integration. So we have two integrals here. One where the integrand is cos t to the power of 5, and one where the integrand is t squared sine t. So let's start with the first one. Have a quick think about how would you progress here. And again, like I said, not asking to put you on the spot. It's just, you know, an exam feels like that. You're sitting there, you don't have the solutions, so we need to think about how to progress. And of course, we want to do that at the revision stage, right? So if you're not sure, then that is also equally fine. We're going to cover that in a moment. And as a hint, we definitely need to rewrite the integrand here. And in order not to keep you waiting for too long here, I propose this rewriting here. Instead of writing cos t to the power of 5, let's write cos t to the power of 4 times cos t as the integrand. And then we need to use an identity here. And that identity is going to be involving sine t. And you know that cosine t is the derivative of sine t. So now we're heading for a substitution here. And the identity that's going to be useful here is cosine squared plus sine t squared equals 1. Have a think about how that will help. And we have cos to the power of 4, but of course, cos to the power of 4 is just cosine t squared and then squared. So now rewrite this for cosine t squared. That's 1 minus sine t squared. And plug that in here. So as we said, cosine t squared is 1 minus sine t squared, rearranging the above identity, and then we square that again. So this now is cosine t to the power of 4 times cos t here. Like I said, cos t is the derivative of sine t, so now we can do a substitution here. And translate everything in terms of u. Let u equals sine t, then du is sine t prime dt by definition. And so du is cos t dt. Take a little now head start on that part. Translate everything into the new variable u here and integrate. Okay, I have a question in the chat here. Is the exam handwritten or digitally on the PC? Well, it's absolutely handwritten. I have no idea how anybody could do this exam written on the PC. There wouldn't be any time. So exactly like I said at the beginning of the webinar, I'm solving this in the way that I would in the exam. So that's why I'm handwriting everything. So you're going to handwrite, and then depending on, I don't know if you are in a, you know, an exam center where you're sitting the exam, or, you know, whatever that's, or whether you digitally upload that is not for me to say. That has to do with how you're taking the exam. But it's absolutely handwritten. The other question is why we don't provide formula sheets. Well, simply, I would say that is not something to worry about, because with sufficient practice in the weeks and days leading up to the exams, you are going to remember the key formulas that you need. So you need to have practice sufficiently, right? That's the way with all exams. And then that becomes, you know, something that you can then quite easily memorize. Okay. And so let's see how you have progressed here. The integral now becomes 1 minus u squared all squared du. And so now we just need to expand here. 1 minus u squared all squared is 1 minus 2 times the product here of 1 and u squared plus u squared squared. So that's u to the 4 du. And now we see here that we have a simple polynomial here that we can integrate. And so we get u minus 2/3 times u to the power of 3. Remember, we raised the power by 1, divide by the new power, plus 1/5 u to the 5 plus c. And now we go back to t. So u is sine t minus 2/3 sine t to the power of 3 plus 1/5 sine t to the power of 5 plus c. Now on to the second integral here. T squared sine t dt. Have a think about how you would progress. So I have a product here. T squared times sine t is our integrand. And you may be thinking integration by parts. And absolutely, that is going to help us here. Let's jot down the formula here. So what's the essence of integration by parts? Is that we have a product of some function f and the derivative of some function g. Now, in this case, these are functions of t. And remember here that the labels don't matter, whether you write uv prime or, you know, VU prime, I don't know. That is the same, right? It's just a label for, like I said, the product of some function, call it F, and the derivative of some function G. And the point is that this is equal to Fg minus the integral of F prime G dt. And the goal here then is that when F prime G is the integrand, we'll be able to integrate, or as you'll see in this question, we may need to do a repeated application of integration by parts. And of course, the by parts formula comes from the product rule of differentiation. So that can be an exercise to make sure you know how to work that out. If you find this difficult to remember, well, then you can always derive it from the product rule of differentiation. Now, the only task left then is to look at our product here and say, what's going to play the role of F and what's going to play the role of G prime. No matter what we choose, it's not like there's anything wrong with interchanging the role of t squared and sine t when it comes to F and G prime. But you're going to see that if we make a selection that's not optimal, but then this here integral F prime G is not going to be any easier than the original. So, but nothing wrong with trying both ways. But I'm going to let F equal t squared here. Why is that? Because then I know I'm going to differentiate F, and that power will come down so that instead of being a quadratic t squared, I'm going to get 2t, and that will not quite work, as you will see, but then we're going to do integration by parts again, and 2t differentiated is the constant 2, and then we're in good shape. Whereas so G prime is going to be sine t. When it comes to this, cosine and sine, differentiated or integrated, you know, they just alternate between each other with a sign difference. So nothing much is happening to those in that regard. They stay trigonometric. Okay, so with F, with that selection, F prime is 2t, and then we integrate G prime to find G. Well, sine t integrated is minus cosine of t. Now, the way I remember it, I remember that the derivative of cosine is minus sine, right? So when we integrate sine, we get minus cosine of t. And whatever you have here for your G, well, we can just differentiate it again to make sure that indeed we're going to get sine t. That's a way to check that you've done the right integration. Okay. So progress with that just a little bit, just to see that you're happy applying this and see what you get. You can put that minus in front there when we do FG. Then we have minus t squared cos t. And then look in the formula, we have a minus here. And the reason I write out this like here with f prime g is that I know that f prime g is my new integrand. So now I have that all on one line, right? So it's 2t times minus cos t. But I have a minus here in the formula. So let's write plus directly so that we don't make a mistake with the sign. Of course, I could put the constant 2 outside the integral here, but I'm just gonna, since we're doing revision, show precisely what we're putting in here. This is the f prime g where we now, but we have changed the sign there since we had another minus sign there. So it's plus now, this integral here. And this is exactly what I talked about. We can't integrate this directly either. We have yet another product, 2t times cosine t. But now we see that if again, we're going to let the cosine function be g prime, 2t is going to be f, so that we differentiate that 2t, and now we're down to a constant. And now by applying integration by parts one more time, then you're going to have the final answer. So just take a moment to do that part yourselves. So you want to hear, let's f equal 2t g prime equal cosine t, then f prime equals 2 and g equals sine t. Since cosine integrated is sine, remember sine differentiated, sine t differentiated is plus cosine t. And then we carry with us everything that we had in the first part. Now we need to do plus fg. That's 2t sine t. And now it's minus the integral 2 sine t. And now we are ready to write down the final answer. And just remember, as we said, when we integrate sine t, we get minus cosine. So again here, now we have plus 2 cosine t dt. And if you want, you can take cosine t common factor. We don't strictly have to, but for this bit here, if you want to write it in a simpler form or in a slightly factorized form, we could do this here. Now, I had a question in the chat. Is it fine to take from the first integral 1 minus sine t squared as u substitution? That will not get easier. If I have time at the end, I'll go through and show it, but it's not going to get easier if you do that. If u is 1 minus sine t squared, then du is minus 2 sine t cos t dt. Remember, you have to apply the chain rule there. So if you try and write that out, you'll see that it won't get simpler. And somebody asked also in the chat, do we focus on these kinds of questions that we're solving in the webinar? No, absolutely not. All the topics are examinable. So these are just representative of some of the topics in the course and how we solve them. So I don't know what the examiner has put on the exam. So they're only representative. To prepare well for the exam, you should cover all topics. So let me make that very clear. Now, next question, the balance in a savings account ST varies continuously with time according to the differential equation 1 over r ds of t dt minus s of t minus k equals 0, where r and k are positive constants. Find in terms of r, k, and p the solution of this differential equation that satisfies s of 0 equals p, where p is a positive constant. And so writing this here, multiplying both sides of the equation by r here, to write this in a more suggestive form, let me write plus and then minus r s of t, and then send that k to the other side here. Like so, we see here that this is a linear first order ODE as follows. And here, the functions p and q are simply constant functions in this example. So the first thing we do is to find an integrating factor. Which is given by mu of t equals e to the integral p of t dt. P of t is minus r. So integrated, that's minus rt. So that's our integrating factor. Just let me quickly check. Somebody said there's a dt left after integrating. That is wrong, isn't it? I was talking at the same time and I wrote dt. Thanks for pointing that out, Joyce. It should be like this here. Okay. Now, we now know here that the general solution is given by the following. The integrating factor mu of t times s of t is equal to the integral mu of t times q of t. And so let's put in our mu of t. And our q of t here. And remember that r and k here are just positive constants. then we integrate here the right-hand side, which is going to give us minus k e to the minus rt plus c. And now we can multiply both sides by e to the rt so that we make s of t here the subject. And c is some arbitrary constant. And then we have the initial condition s of 0 equals p, which gives us that p equals minus k plus c. And so c equals p plus k. And so now we can substitute that in there. Like this here. And now we are at time here, I see. So this webinar is supposed to be 90 minutes. So I will just go through one more question here quite quickly. A function f is given by f of x and y is y to the 4 minus 8a squared y squared minus x squared plus 1, where a is a positive number. And we have two tasks here. It's to find the stationary points of f, and then for each stationary point of f, we want to classify it, meaning we want to determine whether it's a local minimum, a local maximum, or a saddle point. Now, stationary points, as we talked about in the Lagrangian, well, they satisfy that the first order partial derivatives of f with respect to x and y respectively set equal to 0. Well, this simultaneous system here is classified, is satisfied, sorry. So noting that the first derivative here of f with respect to x is minus 2x. Remember, we now treat y as a constant. And fy, we treat x as a constant, and you're going to get 4y cubed minus 16a squared y. And so that's the simultaneous system we need to solve. These equations are actually independent of each other. The first equation tells us that x equals 0. And the second equation here, we take y common factor. And we can take a 4 outside as well here. And we get 4y times y squared minus 4a squared, set that equal to 0, which means that either 4y is 0 or y squared minus 4a squared equals 0. So y is 0. Or y squared is 4a squared, which means that y is plus minus 2a. And so there are 3 stationary points here. We get 0, 0, 0 plus 2a, and 0 minus 2a. Remember, a is a positive number. And then to classify these, we find the second order partial derivatives. So take fx, differentiate again with respect to x. That gives us minus 2. Take fy and now differentiate with respect to y again. And we get 12y squared minus 16a squared. And now take fx and differentiating again with respect to y will give us 0, which of course is equal to fy differentiated with respect to x. And now the Hessian, which is given as follows, is the fxx times fyy minus fxy all squared which gives us minus 24 y squared plus 32 a squared. And then we evaluate the Hessian at each of the stationary points, starting with 0, 0. The Hessian is 32a squared, which is positive since a is a positive number. In particular, it's not equal to 0, as given in the question. And then with a positive Hessian there, we also check fxx at the stationary point 0, 0. Well, that's negative. And so 0, 0 is a local maximum. Now, when it comes to the remaining stationary points, so 0, 2a, and 0, minus 2a, I'm just noticing here that when it comes to the Hessian here, well, the y is squared. So plus or minus 2a is going to give me the same number. So I can actually deal with both of these in one go. You don't have to, but it saves a little bit of time. Okay, well, here, this is definitely a negative number. A squared, as we said, is positive since a is positive. So this product here is definitely negative. And when the Hessian is negative at a stationary point, well, then the point is a saddle point. Okay, so that leads us to the end of this webinar. So we've solved several exam style questions here, like I said, focusing on showing the working very clearly as we go. So as you do revision, practice that. You have several examples in the course you can practice on and exercises. Of course, also review past exams a few years so that you are familiar with the style and format of the exam. But remember, all topics are examinable, so make sure to prepare all topics well is the best strategy. And when you come into the exam, then remember, focus on the positives. So think of grabbing marks, solve the questions first. If you like, you can pick questions that you feel particularly familiar with. And if you get stuck on a part, then you can always come back to that later. So again, this recording will be posted on the VLE by the LSC team within a couple of days. So with that, let me wish you a very good luck with your exam preparations and all your exams. And I hope you've enjoyed the course, and good luck with the rest of your degree program at LSC with the University of London. So thanks again for joining today. Thanks, everyone.